All right, it's our first machine learning design pattern that we're going to talk through in detail, go over a system that somebody may have worked on or may not have worked on. We won't say if it did happen, it was a long time ago, and many of the details of what the people working on a similar system to this today would have been different than what I'm going to talk about here. But I just want to share some of the things that you have to go through when looking at putting machine learning into a working system and figuring out that just naively using machine learning isn't going to get you what you want. And this example is going to be about running a large scale, internet scale, gigantic scale email service. So let's just go through a quick overview of what that means and what the scales are like. You have people who are going to be sending email to your users. You have the user interface your users are going to use. And you have some kind of like service machines that process the email and get them to where they need to go. This isn't going to be about the architecture per se, but it's easy to imagine that you're getting hundreds of millions of messages per day. Hundreds of millions, maybe billions, a lot of messages. And many of those are going to be spam and abusive. We'll get into some details about why that's the reality of the universe. But because of that, you need to run a filter. You can't just take raw email and deliver it to your users. You'd have no users. They'd get sad and they'd leave. So you need a filter. And what the filter does is it examines the messages that come in and it decides if it's going to deliver the message to the email store so that a user can later come along and see it, or if it's just going to put it in the junk store, or there's a third case, which is very common, which is to just delete the email message altogether. But I'm going to kind of leave that out of the diagram here. So then you'd have tens of millions of user interactions with email per day. So that's really a lot of observations of how users interact with email, which emails they interact with, which ones they decide to reply to or delete without reading, and all sorts of crazy implicit information you could use if you wanted to build, some kind of a machine learning system here. So we have a lot of the pieces in place. We have plenty of scale. But we are trying to stop abuse here. And so before you even get started, you have to understand to some degree what problem are we really trying to solve and what are these abusers after? There's a couple of categories of abuse. You could have people who are trying to do crime or espionage or influence elections or state sponsors of attacking particular high-profile users. You can have all sorts of crazy stuff like that. That's maybe not really abuse. That's kind of something different. And what we're talking about in this talk is not really targeting these people. It's more about targeting the professional moneymakers. And the professional moneymakers are the ones that are working at scale. Crime and espionage is generally much more focused. Well, I don't know, or at least it was when I used to work on this stuff. Another thing that people can do is they can do abuse for fun. A term that was thrown around a bunch was like hacktivist or script kiddies, just somebody who thinks it would be neat to change the front page of Hotmail to something. Or, talking with some hacker buddies, they want to accomplish a particular goal of getting a particular user to respond. I don't know what they want to do. There's all sorts of things that are kind of like these one-offs, and they're hard to go after with machine learning as well, because it's not really clear what the motivation is, and these types of attacks can be quite dispersed and distributed and maybe not really good targets for machine learning. Then there's to make money. And this is where you see the vast bulk of the large scale communication and abuse going around the internet is like somebody's trying to make a buck. So that's what we're trying to stop in the main when we're dealing with abuse at internet scale. Now let's go on and say, well, what ways to make money are there? And just a quick overview. Number one is driving traffic. Turns out eyeballs are worth money, I guess. I mean, you can take a user from their email inbox and send them to a web page that's hosting ads that you get affiliate money for every time somebody views them or clicks them or something along those lines. Or you could use it to scam the ad services to drive fake traffic to legitimate ads and mess with the keyword bidding, stuff like that. You could use it to phish or steal personal information. And abusers have very sophisticated marketplaces for reselling personal information and traffic for that matter. So if an abuser can just find out that your email is actually valid and there's a person there and they seem a little bit interested in an email that talks about Amazon, that information is worth money to an abuser They can take that, bundle it up with 100,000 other people who have similar properties and sell it as a list to other abusers who are going to come along later and do more targeted, focused attacks on those types of people. Compromising computers, this is a malware play. If you can get a piece of malware on a computer, you can then sell that computer for $15, or at least, you could have 10 years ago when I was in this field. But there's a very direct market for taking owned computers and giving them to other abusers so those abusers can use them to launch further attacks. Boosting content, like all the videos that I'm making for this class, boy, would I love to have 100,000 likes on them. But abusers could send emails that trick people into viewing content, that boost the ranking of that content, that gets them into the organic search so that they start getting more traffic organically, kind of get out of this new content dilemma of how am I going to make anyone find this video if the video hosting algorithm won't show my video to anyone. So there's markets for this type of stuff. Suppressing content, similarly, you have a competitor, a competitive product on a marketplace. You want to go there and give it a bunch of bad reviews. That's a little bit less clear how to do it with like spam emails, but there's always an angle, or maybe it's like the people who are doing that are buying these other services and using it to suppress content. And then finally, stealing. If you can take something of value directly, that's better. And you could say personal information in some sense is stealing, but an account, if they could get your account to an online game where there's digital content that's worth money or something along those lines. So this is a bit of a catalog of what abusers are trying to do, and when they're doing it, what are they really trying to do, which is like, how are they going to monetize their activity? Very important to understand as we get into what's the role of machine learning in this soup and in this mess. Where would you like to put machine learning to have the most benefit at discouraging people from taking these activities? And it boils down in the email case that basically spam is either advertising for products, so like this driving traffic thing, or it's doing phishing attacks. It's trying to steal your personal information or your accounts, something along those lines, or it's distributing malware, like link you to a site that's gonna, like you go there, there's gonna be what's called a drive-by attack. So a lot of web pages, if you go to them, back in the day, I don't know, like when ActiveX was a thing, I think modern browsers are much better, but there was a time when you go to a website, your computer is owned. There's malware on your computer. You didn't click anything. You just loaded a web page, drive-by attack, no good. Now it's more like social engineering malware, like download this program to update your something, and they try to trick you into getting malware. And then probably the people doing spam would either use your computer to launch further attacks, or more likely they'd just be like, I don't need a hacked computer. Let me sell it and just get on with my life. That's a little bit of the context which you would need to get when you're looking at using machine learning in any application. You don't just dive in and be like, well, what's the first most obvious classification thing I could do? Let's do that. And in fact, the next few slides are going to go through some possibly person that you might or might not know, and their experience going from a brand new person working on their first job as a machine learning person to the most abject failure of their career. So let's go through this for the next few slides. Maybe not though. That person's probably had other failures that you might put up. Let's get started. If you look at this architecture that we talked about, well, how would we take this closed loop pattern approach, and just inject it directly into this system? And remember, the closed loop pattern is where users produce training data for your algorithm simply by using the system as intended, or maybe with a few little tweaks or targeted questions that help you better interpret what they're doing. The email senders launch a new spam attack. So one of these abusers trying to drive traffic, they create a new email about the product they're trying to drive traffic to, they send it to the site. It gets hit by the filter, but this spammer isn't terrible. This spammer has created an attack that beats the filter. We'll talk a little bit later about how they do that. So this spam attack is going into users' email stores. Now, users encounter this over time. That is, as they come to their account the next day, or when maybe they get a notification on their phone, they check it out. Like the spammer may send an entire campaign, and then it may take several days or a week for every user who's going to see that campaign to actually see that campaign. And when they do see it, There's a lot of things a user could do that could give us an implicit signal that the message is spam or shouldn't be in the inbox. One of them is that they might just delete it without opening it. One is maybe there's a report this as spam button that a user might click, or stop receiving this like type of messages from the sender in the future. I mean, there's all sorts, like block the sender, all sorts of things that you could do. Another thing that a fictitious team might have done is to create a actually totally unbiased sample of questions where you take users and you ask them for like 0.1% of the mail that they would have received. Is this something you would have liked to see in your inbox or not? So you can get very, very good labels from either like creating a whole system to ask users questions in a controlled way that doesn't bother them too much, all the way down to just implicitly assuming that when a user reads a message and responds to it, that's something that we were happy to put in their inbox, or they were tricked. But when a user deletes a message without reading it, or just looks at the top of the message and doesn't scroll, or some that type of stuff, then that would be a message that we wouldn't want in the inbox. So in whatever way you're talking about this, you create a label set of various quality, or maybe multiple label sets from each of these different methods. You have your purest labels, but then you also have labels that are less and less pure. Remember in the first lecture, we talked about supervised, unsupervised, and semi-supervised. And here's kind of like exploring the notion of what semi-supervised means, where you have just tons and tons of mail that has no label. Then you have like 0.001% of the mail that has really precise labels because you've asked your users a precise question. Then you have lots of other messages that have various degrees of quality of label, and how do you want to use these. But we're not going to talk about that part of the problem in the rest of this talk. We're going to talk about different parts of the problem. There are many problems. So anyway, you have a training set, and then you can create a model creation environment. You have your orchestration team deciding, we need to deploy a new model every 30 minutes, every hour, every day, whatever it is. And they push a new filter up into the service, and then that spam attack stops getting through. So there you go. I have the rest of the animation. It starts going to the junk folder. Haha, there you go. So that's the closed loop pattern for abuse. Now, let's talk about some problems potentially with this. One big risk, and I know we've talked about this in the discussion times, but I want to go through it again in more detail. One big risk is that this isn't an IID sample, like a message that arrives today versus a message that arrived 2 weeks ago versus two messages that arrived today. They have relationships between them. Right here is a simple chart talking about time and how much data you have, or what type of data you have, or something along those lines. And you could say, well, let's randomly sample among all this data to create the training, the validation, and the test set. Didn't draw a validation set, but you guys know how to split up your training data to accomplish your goals. And you could say, okay, fine, you just pull from all these places. Fine, you just pull from all these places. What could go wrong? Well, it works, like I just said, if all your data is truly IID, independent and identically distributed. Of course, in this case, we can all see that it's not. That line there is your total mail volume. Here's your good mail volume. And it's possible that like all the messages in this place are about Thanksgiving, or all the messages in this place are about, get your New Year's Eve plans set up, or something along that line. So if you pulled training data and testing data from exactly the same kind of like legitimate campaigns, or the legitimate communications, or communications about COVID or something like that, and then, actually deployed the model over here, you are going to be misunderstanding the generalization properties of the model that you learned. But that's just one part of the problem. I mean, it's actually very clear if you look at spam campaigns and the way spammers work. They tend to find something that beats the filter and then blast it. Find something else that beats the filter and then blast it. So if you're getting training data and evaluation data from the same spam campaign from the same spammer, which is a very common thing to do because a spammer can be gigantic in scale. And this is like, in some sense, this is a little bit obvious, but it's also not obvious, right? Like, I managed a person. I came to a team. I was sort of new on the team. I was the new manager, and one of the machine learning scientists did exactly this, where they just randomly broke this up into training and testing data, and then they evaluated it. And here's what was happening. Nobody really knew. I mean, this is kind of, it's subtle. It's not super subtle, but it's a little subtle. And a manager or a program manager on the team isn't going to know the difference. And this machine learning scientist, who's actually very good, had a presentation, brought in all the managers and program managers and said, hey, I've just beat this particular type of abuse. 99.7% of the attack is gone, and my false positive rate is like 0.0001% or something like that. Like the point goes over there. Like that kind of goodness. And everybody was excited. Everybody started working to ship it. And, you know, you had to put the brakes on things and say, hey, let's go reevaluate this. It's just a thing that's going to happen that you need to be aware of when you're looking at any kind of data stream mining. But in particular with abuse, it can be quite bad, because this spam campaign isn't trying to be like hard for machine learning to catch. It's only trying to be hard for the machine learning algorithm that's running right there to catch. So you can be very much misled. So what would you do instead of that? You would draw things right under your head. You would partition your training data instead by time, but also maybe even more than time. You might partition it by sender, so that the same email source, the same IP address that sends mail appears either in the training data or the testing data. And further, you don't have, right, like you do this time split. So you would say, take one set of your senders for this time range and a completely disjoint set of senders from that time range. Now you're starting to talk about how is this model going to generalize in this range, something along those lines. So this is better, but it's not perfect, because you can see on this particular spam campaign that it's possible that spammers don't just send from one IP address. When they send a campaign, they're going to send it from like hundreds of thousands of IPs. So even partitioning by IP address as a sender, you're going to pick up some of the campaign in your training data and some in your test data. So fine, it's better. But you can add a time gap. Like you could say, hey, we're going to wait a week, something like that. And all of these messages aren't going to be part of the testing set. It has a lot of disadvantages. You're trading off a great potential deal of accuracy of your model by adding a time gap in here, but you're increasing your ability to measure what is the real generalization property of my model. So you might consider having a time gap when you're developing the algorithm that you're going to use, because that time gap would let you not get tricked by these overfitting problems or the memorizing the active campaigns, because you have that time gap as you're doing your hyperparameter sweep. But then when you're shipping production models on a day-to-day basis, you might throw away the time gap and just be like, look, man, use the latest mail. I don't want to measure the generalization anymore. I've already been running this system for a week or a month or a year or something along those lines. I just want to get the best model I can out the door. So in that sense, there's places for measuring, like when you're tuning hyperparameters, when you're tuning the system, and there's places for performance, and you don't always need to do everything perfect when you're doing performance time. Another example of that is when you're setting operating points. When you're setting your operating points, you're trying to find the thresholds for your operating points. You could, for example, in this figure, you could reserve a few days of data to set your operating points. That's okay. It would be probably more accurate to actually achieve the false positive rate you're trying to achieve, or whatever you're trying to achieve with your operating point. But that means that there's a few more days that a spammer can be sending a campaign that's defeating your system before that campaign shows up in the training data and you have a chance to start beating it. And remember, there might be a lot of stuff in training data, so you'd need maybe more than just a few samples of a new spam campaign before you get enough evidence to Anyway, there's just a lot of constraints. Anyway, one thing that people can do, which I certainly have been a part of doing, is that you set your operating points on your training data. Sounds crazy, right? Like, how is this going to generalize? And the point is that when you're shipping an anti-abuse model day by day, you're not worried about measuring generalization. What you need to do is say, look, I know that by setting my operating point on training data, I'm going to be more optimistic than I should be. The false positive rate I achieve is going to be not the real false positive rate that I'm going to see in practice. How can you compensate for that? You just set a tighter target on when you're setting your thresholds on the training data than you would if you were setting your thresholds on real holdout data. So you could say, hey, look, I'm I'm not going to go for 0.01%. I'm going to go for 0.001% because I know I'm making this sort of mistake. And then downstream, I know that running a model with that as the threshold setting process in practice is something that my users tend to like. So it's all fine. I don't really know what false positive I'm setting it to, but my users are happy. Okay, that's something you could do, or you could do more partitioning by senders and leave out certain senders here. And I mean, you can go on and on. I think the point is that you guys have the concepts to understand if I need to drive a little bit more performance in one direction, what are some of the compromises and trade-offs I can make in the things that are like technically supposed to be the way to do something, but allows me extra flexibility to achieve the goals that I'm trying to achieve. So this is one thing that could go wrong, right? Like if you're just doing that closed loop pattern, this poor, hapless machine learning scientist in his or her first job about to make a terrible mistake. But that's not the real problem. Let me show you what the real problem it was, could have been, possibly would have been, I don't know. In practice, this is what's going to happen if you're doing anything to stop abuse and you have one tiny little itsy bitsy impact on anything the abuser cares about. Watch. So you get a job, somebody gets a job, and this is the situation of the world. On this axis is days since the person started their job, for example, I don't know. And on this axis is the outcome measure that we might have been using to gauge how well our machine learning and UI are working together to give the user a good experience. And that is the average percent of a user's inbox that's spam. On this chart, look, I left off the labels, but on this chart, I mean, there's a lot of lines here. You might say maybe this is 20% of the average user's inbox is spam, or 15%, or some reasonable amount of most users' inboxes might have at one point in the early 2000s been spam at some email server. I don't know. Right. So what are you going to do? Well, of course you're going to do machine learning. So you come along and you say, well, there are sort of some machine learning systems here, but we can do much better, right? Like there are modern techniques. People have all sorts of great new approaches. Let's bring some of these, the fancy, shiniest thing to bear and solve this problem. We'll look like a hero. And besides, I hate spammers and everybody will be happy. This is going to be great. I'm so glad I took this job. So, it's pretty obvious that the content of spam, I mean, you can look at the content and it's spam. Look at it. It says Viagra right in the subject. This is spam. Don't deliver it. How hard can this be? So you do great feature engineering. You do all sorts of tokenization, normalization, new feature word breaking and translations between encodings and non-encodings, crazy levels of depth in your feature engineering, your tokenization, the n-grams, all of this stuff. And then you're also, like you took the bounds lecture, you understand what the binomial distribution is and what error bars are and how to calculate them. Variance standard, you got all that stuff. So you compare your new approach to the current model and you crush it. You are on the ball. You've got this thing nailed. But that's not good enough. You want to do even more. So you flight it. Everybody talks about flighting. Flighting's the best thing ever. You can ship this to a small number of users and run it for quite a while. Let's say you run the new model for a month, and then you see that those users who you've shipped it to are having more engagement. Their inboxes are much less spam, and that's leading to better sentiment scores. And you're like, we really nailed this thing. Oh my gosh, this is so great. How did I do all of this in only 50 or 60 days? Something along those lines, or whatever. So then you have to go and do all the engineering to productize it so that you can go to scale. And that can be a darn lot of work, to take something that you're running for a few users and run it on tens of millions of users. But okay, fine, you do it. You are very sure, you're very careful, you work with a lot of people, you ship it to the entire site, and kaboom, you nail it. The most users' inbox spam is cut about in half. Everything is great, amazing success. And I have some advice for you. If this is where you are, make sure you get your spot bonus locked in right now. You have like very small number of days. Get that locked in, or make sure you ship this right around when they're having those calibration meetings for your next review. You want calibration where this circle is. Calibration meetings right there, because what's going to happen? The abusers are going to come along and notice and say, hey, I'm making a little less money today. Maybe I should put down the Mai Tai, get off the pool chair, go to my computer and spend 15 minutes tweaking my Python script that generates my spam messages. And they do, and they might have in the past. And then over the next couple of weeks, you may see something like this. So it's a total failure. That's bad. Then you keep running your machine learning system and you're like, oh, no, it was just a fluke. It's whatever. It's going to just give it some time. You can run it for weeks, months. It's retraining. You're shipping more models on the right-hand side than you were shipping on the left-hand side. You have a lot more cleverness over there. And it had no effect. Nothing's changed. And all you're doing is spinning CPUs, burning model training capacity, and not accomplishing anything for any users. Why? What happened? Why? Well, turns out spammers are actually pretty smart. They probably know as much machine learning as you do or I do or whatever that is. And they want to make money. And they're very interested in money. And it's not that hard for them. So they notice that something about the site changed and is now blocking a lot of their campaigns, and they're unhappy. So they send thousands of messages to accounts they own. They've created accounts. There's no way you can stop them from creating accounts. Even if the accounts cost like $1 a piece or whatever it is, it's probably worth it for them, and you'll never find all these accounts. So they send thousands of probe messages to accounts that they own. And then our system dutifully classifies them, either throws them away or delivers them to the inbox of an account that an abuser owns. Then the abuser just scripts it and says, okay, well, let's figure out which of my messages got to the inbox. And these messages, they can be like a spam campaign that the abuser wants to send, add some words, take away some words, different product, same product, different image, same image. So they're probing and they're trying to find what are the boundaries of the decision space that your model is creating. They script it, and then they can do more than that. They can create their own training set. And this is a training set of what tweaks to a message get around the filter that this particular email service has live today or at a particular time, or over a period of time. They can start to learn the types of messages that you pick up on and the types of features that maybe your service is blind to. Like, if they encode URLs, do you ever pick up on those? Or are those completely outside of what your current filtering system is considering? Then from that, they can train an anti-filter. So they can build a model that mimics what your system's going to do, and they can use that iteratively to craft the next spam campaign that they're going to send. So they can be like, well, this message defeats the filter, but it doesn't look as good. So let me change it to have a higher conversion rate by making the ads more prominent or something like that. Check it against a filter. Ooh, that one's getting caught. Okay, let me change it a different way. So they produce the campaign that they're going to want to send, that they think is going to achieve the goal that they want to achieve. And then they launch the spam apocalypse. They can send more spam in like minutes, weeks, days, seconds, whatever it is. They have a lot of IP addresses. They have a lot of bandwidth. They have a lot of capacity, or they're not professional spammers. I mean, we're talking about people who are making businesses at this. If you're doing things at scale, you're going to have to realize that you're dealing with smart adversaries. Ugh. And then all this stuff goes straight to the inbox. Your filter doesn't catch it. Ugh. And one way to think about it is that spammers are in a very strong position because this closed loop pattern has built-in latency. It requires users to get the message, to filter it, for you to build a new model, for you to get enough of the new campaign in the new model for you to start catching it. Whereas spammers just work on scale, which is like, let's get that to the inbox as quickly as possible. And their scale is small compared to the scale of your site. So it's not like you can just be like, ooh, look for a spike and then shut it down. So, okay, this is the problem. Now let's talk about this some more. Why the heck did machine learning fail? And maybe this is obvious by now. Hopefully a lot of this is obvious by now. But if you look at on this axis is some notion of the feature representation that our filter supports. And on this axis is something like the percent of spam for an instance with that particular representation. So you could say this is like the most common feature vector for spam emails. And then this is a feature vector that has basically 0% spam. That's where good users are sending their mail from. So if this is day one and you're going to build a model, you can say, well, I'm going to use machine learning. But here's the assumption that's baked into the machine learning, that every sample I pick in the future is going to follow this distribution. So when I pick a new email message a week from now and try to classify whether or not that's spam, whether I should send it to the inbox or not, as long as it follows this same distribution that I trained on, it doesn't violate my assumption, I'm going to be able to know how well I generalize to that and everything's going to be great. But you can deploy that model, and you won't be perfect. There'll still be a little bit of spam, so that green thing is not an exact lineup with the distribution of spam. That's okay. That's your generalization error. That's your model representation, your underfitting, overfitting, whatever it is. But spammers don't care about that. They just say, oh, you're blocking that part of the instance space where I used to be focusing my spam. No problem. I'll just do something different. And spammers can overnight completely violate your assumption and destroy what you were talking about and completely work around a filter. And maybe you could have another axis, which is what's the conversion rate of spammers in these places. Like maybe the ads are less appealing to users, but it turns out that has never really affected any spammer that I bumped into. So what spammers have done is number one, they attack your vocabulary. They put words in their spam messages that you didn't feature select when you did feature selection. That's a very easy thing to do. There's more words than you'll ever feature select into a model. Even if you're using 100,000, 200,000, there's many, many, many more words than that. But not only that, you can do misspellings of words, and people can generally, they won't even notice a misspelling. I mean, believe me, I don't notice half my misspellings. They can also do token attacks, like put punctuation in weird spots and try to attack how you're breaking a sentence into words. I've seen a lot of things where they'll put like hidden HTML tags. Like if you're going to do hello, then there'd be like some hidden HTML tag here that's a comment or something like that. And a token breaker might break this as he low, whereas what they were trying to say is hello, things along those lines. Another common attack is to just take content and put it into images. If you have an email with an image, which is all of the spam message, followed by a bunch of text, which looks like a totally normal message between you and a friend, but there's just that little image that has all the problem in it, and the interface is going to render that image to the user, but your spam filter doesn't have time to render all the images and do OCR and all that stuff. You could potentially have a problem. Another thing they could do is just straight avoid the model. And that's kind of what I drew over here, where they just send different instances. Like these are instances that are perfectly valid spam instances in the space, in the feature space that you've created. It's just that your model never trained on them. You never knew to put a probability that thing was going to be spam on them at all. They could mimic good content. That image attack is something very similar to that. And then rapidly change and just keep doing this. No matter how fast you move, they're going to move faster. No problem. Right? Like, So our first approach to fighting spam was terribly wrong. I mean, we thought we knew what spammers were going after. We thought we knew that machine learning was awesome. We thought we knew just where to put machine learning. Totally wrong. So let's revisit what spammers are doing and try to think about this a little bit more carefully and come up with a little bit deeper insight of what mistake we made. Now, I'm sure all of you guys are clever, smart. This spam stuff isn't brand new. You probably have 6 or 7 ideas of, well, how do we make little tweaks? Like, why not run the filter on things that are already in the email store so we could time travel and that would make things better, right? Like, but let's get a little bit more fundamental to what's going on. Not that that's a bad idea, but I'm just saying, let's spend a little time here. And abuse is a business. And that's one thing I learned very clearly over my years working on it is they're just business people. Like everything, they want their expected return to be greater than the expected cost of starting a spam business, of creating a spam campaign, of advertising for a new product, of creating a new relationship. Everything that they do, it's about figuring out, am I going to make money on this or am I going to lose money on this? And so you just have to assume they're going to do that well. So let's break this down. What is the expected return for, let's say, a spam campaign? You could take the value of a conversion. That is, every time a user is tricked or, decides to buy whatever it is that you're trying to sell, you're going to make $1. You're going to make $5. You're going to make $15. Whatever it is, depends on the marketplace that you're selling into, the value of those types of things on that particular day. But, that's an important point. Then you have to multiply it by the conversion rate. That is, for every impression I get in front of a user, what fraction of those users are going to be like, yeah, I want that. That's for me, right? Like, ooh, really? My computer does have a problem. I better visit this website. Like, what percent of users are you going to trick? And then what percent of your campaign is going to get to the inbox? So let's say I send 100 million messages and 1% of them are going to result in conversions. That's 1 million conversions, and each conversion's worth $10. A lot of money. Those aren't the correct rates exactly. Or let's dig in a little bit more. And like I said, they have all sorts of infrastructure built up to collect money from conversions. Affiliate marketing, you can probably go search for this and find websites, or even like, I have this YouTube channel, whatever, and I have an Amazon affiliate link. So if I talk about a product in one of my videos and I put a link to the Amazon site with a special encoding to it, and you follow that link and buy that product from my video or whatever it is, I make like 20 cents or 2% of whatever. I don't even know what it is, something along those lines. But then there's all sorts of abusive affiliate networks that will sell Viagra conversions or sell get a membership to a porn, whatever it is, they'll sell it. And so anyone can come along. You don't have to develop the product. All you need to do is go and find one of these affiliate networks, become a member there, pass whatever it is to make sure so that they know you're actually a spammer and not somebody who's going to try to rat them out, whatever it is. I don't know. It's not even really like illegal. It's just kind of shady. Compromised accounts are a little bit more shady. You can make a few dollars for every back in the day, Windows Live account that you could sell. It could be like $1, $2 or something. If it's a legitimate Windows Live account, there's a website you can go, you upload the account name, the password, they send you $1. That's all there is to it. That's very easy. So the conversion can value from a few dollars to if you're getting malware on a machine, like I said, it could be $10 or $15, something along those lines, just depending on the attack. The conversion rate is low, 0.5%, maybe even lower than that. That's one of the things about this business. It's about all ad businesses. You're going to have low conversion rates. And then if you're dealing with a sophisticated spammer who's constantly trying to work around your filter, they might expect to get as much as 1/4 of their campaigns into the inbox. That's not great. And again, all these numbers are pretty far out of date, but just, the thought process. If you're working on a similar system, these are numbers you should really understand, right? If you're building anti-abuse, you're doing machine learning, you don't know these numbers for the markets that you're involved in today, you're doing it wrong. So there's a lot of economics, a lot of subtlety. You could talk about like Say's law, supply and demand, exchangeability of product, elasticity of prices. I don't know. I'm not an economist, but the mental model that I sort of had for a while is that a spammer could make about 0.1 cent per email they get to the inbox. So 100 emails to the inbox, they're making a penny. 1,000, they're making 10 pennies, whatever that is. So not that great, but not that bad. If a computer's doing all the work and you can just scale it up and you built this system to do machine learning to figure out how to get things to the inbox, not that bad, right? But let's go through that part of the equation in a little more detail. What are the expected costs? You have the cost of delivery. How do you get the message to the inbox and then collect the conversion? You have the cost of creating the content that beats the filter. And then you have the cost of finding who you're going to send your email messages to, their email addresses, something along those lines. And to just kind of short circuit some of this, these are small fixed costs, like basically zero marginal costs. That once you've set up your business, once you've got your list of 100 million, whatever it is, however many people you're going to send email to, you can buy them. They're pretty cheap. You buy enough email account, like verified email accounts for legitimate users from, again, one of these marketplaces. Maybe you spent $1,000, $5,000. It's basically nothing in the scheme of running your spam business for the long haul. And then, like we talked about, setting up the probe accounts, all that. Maybe it costs thousands of dollars. Maybe it costs $10,000, $15,000. You're in the spam business. But then for every campaign you send downstream, all that same infrastructure is working for you. So you're in a pretty great shape there. The problem is, what does it cost to send the spam? You have to buy bandwidth, and you have to buy bandwidth that has access that's not already on some internet known block list. So you have to find relationships with people who can create you this infrastructure that you're going to need and keep it fresh over time. And then, of course, you need somewhere to direct the conversions to, and this somewhere needs to be a place that hasn't totally been filled with spammers, so everybody knows about it and can like identify that, hey, don't let people direct my users there. That's not good. So the net of this is that an abuser needs about 1,000 messages to the inbox per dollar they spend buying this part of the problem. And that's the incremental cost as they continue doing their business. And that's the part of this that we really need to attack if we want to stop spam. Now, there are other parts of this equation that you could consider attacking. Really interesting person I worked with in the early days had a great idea. They're like, well, why don't we attack conversion rate? And here's how we do it. There's certain users on our site who are gonna buy Viagra, who are gonna click these links, who are gonna be fooled by every credit card offer, by every like, ooh, your computer needs something, right? They're there. Let's say it's 3% of our user base that is interested in those products or just generically easily fooled by spammers and abusers, something along those lines. Well, very simple solution. We find them before the spammers find them, and we kick them out of our network. Gone. You guys are gone. Get out of here. Go to whatever it was at the time, AOL or Yahoo Mail or wherever it is. You are not welcome on our site. Spammers over time figure, hey, nobody on that site ever buys my junk, and they stop bothering. They build their infrastructure, right? They build their infrastructure around monetizing other mail services and not monetizing your mail service. So, right, like that's kind of a silly thing to say, and it didn't get very far. Probably would have worked, probably would have been a lot cheaper than, than attacking this and building that and maintaining it over time. And that's an example of, hey, maybe machine learning wasn't the most efficient solution to this problem. It's just the one that we had to do because the more efficient problem wasn't really ever going to work. Here we go. So content filtering, it's the first obvious place to put machine learning. It targets the things that the spammers can easily change. So we're, like I always say when fighting abuse, but maybe broader than that, don't target what your adversary happens to be doing. Target what they have to be doing. And that's the way that you're going to win. Because if you're targeting what they happen to be doing and you don't understand how much it costs them to change what they happen to be doing, it puts machine learning in a very weak position. It's not a good tool because this IID assumption and the latency of building these internet scale services, it's just a difficult situation to be in. But what about this? What if instead of targeting the content of the messages, you target the reputation of the person that got the message there, or the reputation of the site that the message is trying to direct you to? Those are two sides of the coin in terms of attacking the thing that the abuser has to do and that costs the abuser money. Target the IPs, target the web hosts, target the things that cost them money. Now let's look at this pattern for doing closed loop abuse filtering with machine learning and figure out what would be different if we, instead of primarily targeting content, we wanted to instead target reputation first and then maybe content second. I mean, there's still a role, of course, for content. Let's walk through this. We'll talk about it. So the email sender sends a new campaign. Maybe it's a legitimate sender, maybe it's a spammer. We don't know. But instead of calling a content filter, we call a reputation filter. Now we'll get to in a second what this reputation filter predicts precisely, but we can just say at a course level, if we're talking about kind of like business logic, we'll say, well, do we know that that sender is good? If so, put them to the email store. And notice this bypasses the content filter completely, saying, here's a sender who's been sending mail to us for like 2 years. They've been sending tens of thousands, hundreds of thousands of messages. We've never had users complain about them. Save the content filter CPU. Save the false positives. Don't give those users false positives. Don't give that sender false positive. They're cool. So in that sense, we're carving off the easy stuff. And the problem that we leave behind is a little bit harder, but not distributed across everybody. So the next step is we can carve off the other side of the problem and say, hey, that IP address has sent us a lot of spam. Block it. It's not sending us any more spam. That is it. It is done. So we've carved off the two ends of the spectrum. Now we're left with the middle of the spectrum. And the middle of the spectrum is going to be the hardest part. I mean, this is like where the real fight is. This is where the good spammers will play, as well as our new users who are new to the site and unfortunately are going to have to fight, the new senders that are sending email to us. They're going to have to live in this world for a while until our reputation filter can learn more about them. But now the problem is simplified in that way. And what this lets us do is that we can take the content filter and use it in a much more aggressive mode than we used it before. For the senders that are uncertain reputation, small, new, something along those lines. So one option is to just set a much more aggressive target for them because all of these users have been saved and we don't have to deal with them in the content filter and we don't have to save space in our false positive budget for mistakes that we might be doing on them. And then at the same time, you could use the reputation filter to throttle and slow down things that we're unsure about. In the theory that a new legitimate sender may only send a small number of messages to your site, whereas a new spammer might try to blast their campaign, the spam apocalypse, kaboom stuff. And we just say, look, you can't do that. We're going to even force you to distribute your attack through more IPs. We're going to force you to pay more money to deliver the attack because we've throttled them way, 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 way down. And turning those knobs and turning the kind of false positive, false negative rate of our reputation filter gives us a very strong position to put costs on the spammer. Then we do the same thing, users encounter over time, blah, blah, blah. But now the labels that trickle in we can use for two things. We have content training just as before because we're gonna need content filter. The content filter can even be used, to create some of these semi-supervised labels for reputation training. Like, hey, our content filter is flagging everything from this new IP address. Let's not even wait until users tell us about it. Let's just update its reputation immediately, right? That's a thing you could do. But now the reputation training set might be something along these lines, which is the probability that we'll have lots of complaints by tomorrow about email from that IP address based on the history of the sender and the user feedback that we've seen so far. So that might be the notion of the training problem, the probability estimation problem that we set up in the reputation space. It's not necessarily about spam directly. It's about these user complaints that we're going to see tomorrow. And we'd say if there's an IP address that we have a long, stable history with, and they've been sending a lot of messages to us and we've never really seen complaints, then the probability that we're going to have a lot of complaints about them tomorrow is quite low. It is kind of like the intuition of what we're trying to do here. Then, of course, you would deploy new models just like before. And the thing is that the content filter is unstable because abusers can change what they're doing very quickly. The reputation filter has less of this property. It's a little bit more IID-ish in that, the people who are sending you legitimate good mail are generically going to change slowly. And then it's just these sort of out of vocabulary IP addresses or out of vocabulary web pages. Like, I've never seen this before. It wasn't in my training set. Out of vocabulary is a sign that it's probably spam or a new user that we need to somehow rescue. So this attacks things that cost abusers money, block bad things, throttle unknown. It frees known good senders from potential false positives. And this is an example of the architecture stuff we talked about, the intelligence architectures, where we would say, we have some business logic and it may not be the best exact modeling thing. Like on a particular day, it might be better to combine these two training sets into a single training set, but over time it may not be. And then it changes the game. The goal is to identify good senders as fast as possible, but also to give good senders an out. If we're blocking a good sender, we can give them an escalation path that lets them do enough CAPTCHAs or get a cert or something along those lines. Give us some evidence that they've done something that a spammer could never afford to do over the long run. And if they do that, then we can pop them out of the bad reputation state. So you see, this might even include what we used to call it proof. The proof, P-R-O-F-F, the proof that the user has done or the owner of that identity has done to prove that they're not a spammer by putting on the line some amount of money that we believe would make a spammer not be able to make a profit. So that is another approach to solving this problem. And you can see it sort of relies on two different machine learning models that work well together. Revisiting intelligence architectures, why would you want to structure it this way where you have these two separate models versus, if we start off with probability of spam given content, why don't we just do probability of spam given content and reputation? Well, the problem is a couple fold. Number one is that it's an attack vector. If your model is balancing content versus reputation, there's always things the abusers can do to work around your reputation filter. They can do, one thing's called content stuffing. They can make a message that looks so good that if you combine it with reputation of the worst possible IP address in the universe, the message will still look good. And the problem is that, when you're just relying on machine learning and you're saying this IID assumption and spammers gigantically break the IID assumption by reverse engineering your model and doing content stuffing, they can work around this combined approach. So it puts a giant hole in your system and you're going to be constantly chasing your tail, trying to figure out how to tweak things and make that hole less wide, whatever. One way to do it, simple architecture stuff, simple intelligence architecture, you separate them out. And so you no longer have your reputation filter on a particular message basis be able to be confused by anything that the spammer happens to be doing in the content. Gives you a lot of power, puts you in a much stronger situation, might not be the most accurate on, if you were to train and if IID was real, certainly wouldn't be the right thing to do. But IID is not real. So it is the right thing to do in practice. And then and I drew that proof thing. This setup lets you include in your reputation model a lot of business logic and a lot of controls and a lot of out-of-band information. For example, you could say, as a business, I'm going to give somebody a known good reputation if they pay $10 to some accreditation site and their mail is signed with a particular certification. You could try to trick your machine learning into learning that, but your PMs would be mad at you. You'd be running around in circles trying to, and it's much easier for those sorts of things that you want to communicate externally, tell partners, hey, you can rely on this, but then also be able to tweak the thresholds if something goes wrong. I mean, that's more of a business thing, and this is a great way to integrate those types of properties into your machine learning system in a controlled way and empower the right people to make decisions about how they evolve over time without messing up the whole system. So here's some criteria for deciding, let's just go through this again. The ability to use a loophole in one system to beat the other system. That would be a great reason for you to use this kind of like business logic architecture or like model sequencing or model partitioning, any of the other things that we talked about. Reduction in churn of mistakes. So if you were training a new spam filter every day, even if that new spam filter was better overall, it might move the mistakes around and it might move the false positives around. And so without this reputation filter pulled out separately, you could be a large email sender and every day 2% of your messages get blocked, or one day no messages get blocked, another day 5% of your messages get blocked, something along those lines. So you're going to be calling up, they're going to be calling you, they're going to be saying, why with these mistakes, go do better feature engineering, blah, blah. No, you don't want to spend your life on that stuff. It's a known good sender. Don't try to trick your machine learning system into knowing that a known good sender is going to be a known good sender. Encode that knowledge into your intelligence architecture. Save yourself a lot of headaches and a lot of time. Another one, like we talked about, is the ability to partition across modelers and teams. Maybe you have one person building a reputation model for the sending IP address. You have a different person building models for the IP address of the websites or the domain names of the websites that the email message references. Maybe you have another person looking at images and trying to identify logos, other things like that. Like, this message uses a logo from a known bank. It doesn't come from an IP related to that bank. That would be a good, so you can partition the problem up and create a whole sort of array of these reputation-ish features, and then use some very simple business logic on how they combined to either completely bypass the content problem or completely block or throttle the people sending those types of messages. Then you want to reduce the coupling between the models. Like this right here, this content and reputation whole also is a sign of coupling between types of information that maybe shouldn't be coupled. And to some degree, you're making the learning problem harder because you're trying to tell one learning system to take these two things that are very conceptually simple. Does this message look at the content look like a spam? Does this sender look at everything they've sent over time look like a spammer? Does this combination of these things look like a spammer? That's a harder problem, and it puts coupling and it makes it much more difficult to innovate on either of those parts alone. The business logic, I think we've talked about that to some large degree. And then the real kind of way this all boils down is it's so easy as a person who's getting into machine learning. You have all this math background, all this optimization background. You really want to do the best thing. You want to bring out all those mathematical models you've learned. You want to come up with the most accurate thing. But you really have to remember, accurate on day 1 is not equal to accurate on day 90, day 100, day 300, something along those lines. So you really have to think about the architecture more than the aggressive model. Now, let's just do a quick summary. Key assumption in machine learning is that everything is IID. In adversarial machine learning, you're pretty darn sure it's not IID. It's instead of IID, it's what's ever worst for me. IID, whatever's worst for me, right? That's what the distribution of samples is going to be. Always violated in practice, and it's really always violated with adversarial settings. Naively using machine learning for abuse, it seems to make sense. It will work fine if you're going to write a research paper. It's going to work fine if you're going to try to create an abuse filter just for you. It'll probably work mostly fine. It'll fail completely if you affect the abusers at all. If you take 1 penny from them, they're going to work around whatever you did. And remember, things are very asymmetrical. They don't have to have the infrastructure. They don't have to ship to scale. They don't have to deal with privacy. They don't have to all the things that you have to do to run a big site. You're spending way more money per change you make than they're spending per change that they make. What you have to think about is abuse is a business. It's there to make money. It's not there to play around with filters or machine learning or whatever it is. They're just going to focus on profit. So you have to position your machine learning in a way that targets their profit. Target the things that cost them money, target what they have to do that costs them money. Don't target what they happen to be doing or they can change cheaply. The takeaway from this whole design pattern, the reason that I belabored it so much, number one, it's something I know quite well. So I think it's nice to be able to talk through all the kind of intricacies of how machine learning goes into a system like this. But I've seen it again and again in different domains, is the obvious way to do machine learning is not always the best way. You might be targeting the wrong goal. You're not achieving the outcomes you want. You might be putting machine learning in a position where it's at a real disadvantage. Instead, you want to find the core of what's bringing my users value and where is machine learning really the right tool to use. Like in this case, reputation, better than content. In your case, I don't know what it is, but I'm sure if you just think a little bit more past the obvious thing, you're going to come up with a better answer for where and how to use machine learning. All right, thanks everybody. See you next time.